Welcome back to Advent of Code. We've got, again, a couple of minutes, or actually 60 seconds, before day 4 starts. So as usual, I will cover the refactor for day 3, and then we'll continue with day 4. So I actually already have our benchmark times up here. We ended part 2, day 3, with about a runtime of 250 microseconds, we'll call it. And the refactoring goes down to about 50. The major reason this happens is because we chose to use max set by key from itertools. And what max set by key does is returns all of the matches for the maximum number. So in this case, we iterated over the entire bank. We found, say, all the 9s or all the 8s or all the 7s or something like that. And then that has to be returned from this in some way. And if we click through the implementations here, we can see that the underlying implementation for max set by key ends up creating a result, which is a vec, and then pushing onto that vec and returning the vec at the end. So this allocation is basically what's costing us time here. So we get all of those because we need to get the first max value, not the last one, which is why we're not using max by key. And that means that if we make a change to reduce, so same logic here, above and below, the accumulator and next are both the index and the character. And then all we need to do is check whether the next value is greater than the current value that we have stored. If it's greater, that is the next most first value for that max value. And we return that. Otherwise, we return the one we already have. And doing this gives us the first max value for all of the slices that we need to operate through. And it does it without allocating a vec, or actually many vecs, which again results in a nice performance increase from removing that vec allocation and getting us down to just 50 microseconds here. Now I'm running on a Mac M1, which I know at least is slower than my Windows PC by about 10 microseconds. And it's an M1, so it could be slower than other computers in general at this point. So with that, we're a couple minutes in and we're starting with day 4 printing department. We ride the escalator down. I still don't know why we couldn't have walked down the escalator. Escalators break, turn into stairs, and you can just walk down them. Bunch of decorations and stuff, helping elves again. Forklift optimization. Do we get our forklift certification? Ooh, today's going to be a grid problem. Okay. The rolls of paper at are arranged on a large grid, so ats are blocks. We have our puzzle input here. The forklifts can only access a roll of paper if there are fewer than 4 rolls of paper in the 8 adjacent positions. Oh, great. If you can figure out which rolls of paper the forklifts can access, they'll spend less time looking and more time breaking down the wall to the cafeteria. In this example, there are 13 rolls of paper that can be accessed by a forklift. So this is one full pass, I'm assuming. It's not like once we take this one away, then that frees up another one. That would be a second pass. At least that's my current assumption. So we have our diagram of the paper roll. How many rolls of paper can be accessed by a forklift? So we have a couple of options here. I think this is our test input. Let's just create day 4, get that in here, get our input into part 1. I believe 13. Are we supposed to count the number of rolls? How many rolls? Yeah, so number 13 is going to be our answer. We do need to do some kind of parsing here. There are 2 thoughts in my head. One of them, which is the approach that most people are probably going to take, is to do lines enumerate for loop, and then you get the 2 values. The other option that I do tend to like using is using nom locate, especially when there's multiple potential characters that mean different things. And checking the dependencies, this does support nom8, so we're still good. Basically, the TLDR here is that this would give us the locations as well as the values by just introducing this additional position parser and changing the input type. And down here, you can see this gets the column and so on and so forth. So we could use nom locate. We could use a for or double for loops. I think when it comes to the problem, we have options as well. One of the things that I do like doing one of the things that I do like doing is using a library like glam to represent these locations. So these are 2D locations in integer positions. So we could use an ivec2. This is really nice because it's basically just what I would have created anyway. If we look at the implementation, we've got an ivec2 that's an x and a y. And this struct is like no overhead. So this is literally just 2 i32s. We get a bunch of constant defaults, things like X and Y for the axes, different ways to construct them, etc., etc. So at the end of the day, this is just a struct with a bunch of helper functions, and there's no overhead to actually using it. So really the benefit for me here is that we're going to have an X and a Y and not a .0 and a .1, because I don't know about you, but I forget which position is which position if I don't have an X and a Y. So we've got parsing options. We've got a potential way to, or a couple of different ways to represent the positions. We've got no pathfinding to do currently. We just have to access all of the positions. So actually, probably if you wanted to be fancy about it, you wouldn't even need to parse this, because you could take that original string, you could do indexing in and find different locations here. That's not a particularly satisfying way for me to do it personally, so I don't think I'm going to take that route. I think I'm going to do one of the parsers here. We really only need to check the 8 adjacent positions. So what I'm thinking here is that we bring all of these into a hash map of position. Realistically, we don't actually need to keep any of the empty spaces, not for part 1 anyway. So it could just be a hash set of all the paper roll positions. And then if we can access the values in the hash set, then they count. And we don't need to talk about anything past that at this point. So I think the for loop is something that everybody can figure out on their own, right? For X and, right, it's like input.lines, .enumerate, and then like flat map, line dot cars, .enumerate, and line will actually have the Y position, as well as the line, and line.cars.enumerate ends up having the X position. So this is roughly the parse, right? And here we probably only want to keep the roles. So really this is probably filter map. And we do value equals at dot then sum. And I don't think I have glam here already. No, I'm tracing. I think we have glam installed in our root. So I'll just add it here. And here what I'll do is ivec2 new xy. And we're going to collect this at the end of the day into a hash set of ivec2s, bring in glam ivec2. This is a character. So I'm going to change this from double quotes to single quotes. This flat map has some issue. Let's find out what that is. So basically we haven't brought in hash set yet, so we'll bring in hash set. This says collect can't be called on that flat map because I have a semicolon here is basically the issue. So this says collect exists for flat map. Flat map is the function, or rather the struct that implements iterator that is returned from the flat map function. So if we call .flatmap here, what we get back out of this call that we can then call collect on is a flatmap struct. We're getting use sizes here because of the way that this is being constructed. I happen to more or less know that we're not going to get like use size based things. So we'll do as I32. I feel comfortable doing as here because I have knowledge around how the problem is set up. And this is never going to exceed an I32 amount of storage positions, or our input would be huge. But it doesn't look that big. It's only 100 lines, so we're going to be fine. And then we have some issues with borrowing. Let me open this up so we can actually see what's going on here. This says the closure might outlive the current function, but it borrows y, which is owned by the current function. The current function being our closure. This closure then borrows y because we're using y in here. So the suggestion here is to force the closure to take ownership of y and anything else that it captures using the move keyword. And the Rust compiler is very smart and knows that we aren't using this value. And if we run this and I log out positions, then we should end up with a bunch of output. So our input looks like this, and then our positions hash set looks like this. So really the question here is this the correct numbering? So the first number that, or the first roll of toilet paper, what are we doing? Roll of paper. Is it just paper? Large rolls of paper. They're just large rolls of paper. Okay, we're just going to call them paper. So 0, 1, 2. So we should see a 2, 0 in here. And there is a 2, 0 in here right here. And that is right next to a 3, 0, which also exists, and then a 6, 0, an 8, 0. I think in general, this is good. So let's check one more. Let's see, 0, 1 should also exist here. And 0, 1 does exist here. So I think we're good. Sometimes what I like to do with these problems is write a print that will iterate over these values and then print out the resulting grid. That's usually more helpful when we have more steps. So I probably won't do it right now, but we could do that in the future as well. So we have all of the positions. And now basically what we need is, let's call this neighbors. I think that we need all 8 surrounding locations, right? 8 adjacent positions. So that's all 4 diagonals and all 4 north, south, east, west. Unfortunately, this is one of the cases that we don't have a preset amount of them for, so we are going to have to construct this. So my goal here is to make this a series of these. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. So we need to set up 8 of these in each direction. So we need x, y, we have neg x and neg y, and then we'll need each of the corners. We do have 1 here. So 1, if we look at the source, is a splat of 1, so it's 1 in both positions. We'll also want neg 1. And then we need the combination of x and neg y. And here ivec2 plus ivec2 is non-const, which means that it can't be executed at compile time, which is what this is doing. So we can solve that by just using new instead here. So we've got x, y, neg x, neg y, which are all of the cardinal directions. And we've got 1 and neg 1, which are the 2 diagonals. And then 1 and neg 1 and 1 are the other 2 diagonals. So this is part of the reason that I chose to go with I32s and not U sizes or something like that, so we could execute these negative operations or preset these directions. So now the question is, for all positions, for all neighbors, let's call this offset, I suppose. We need position plus offset, and we need to know if that is in positions. So we have a notification that says that we are trying to add a shared reference to an ivec2 to a double shared reference to an ivec2. So we can dereference our offset, which then will tell us that the value that we have is probably not a reference. We don't need to keep this value, which is really interesting. So the other thing that we can do here is destructure the shared reference off there as well. This again is another indication that our closures that we're using, which capture variables from their environment. In this case, we're borrowing position. And in this case, we actually just need the count. So we don't need to pass this whole iterator back without resolving it. Before I had count here, what I had was an iterator, which needed to be called to be executed. So we were passing back that iterator and all of the references that all those closures captured, which would then obviously need to live for a longer period of time. In this case, we're trying to cut this down to just the count, because we need to know if the positions that contains these is, what is it, greater than 4, greater than equal to 4, fewer than 4. Fewer than 4 says 0 to 3, so less than 4. So if we filter this, this changes slightly the arguments that we get for what position actually is. So this position is now a double shared reference. So we'll do the same thing. We'll destructure that shared reference right off. And then what actual value do we need? The number of rolls of paper. So we need to count this. And then we'll return count. And I will run this. And our test passes, which is great. Let's make sure that I didn't make some mistake and that the test can actually fail, because we never saw it fail. And now we have a cargo run for day 4, bin part 1, which gives us a number. I have no idea if this number is correct. We're going to find out. And it is. So we have a gold star. So this consisted of basically 2 phases. Our first phase was just collecting all the positions that had a roll of paper at all. And we basically did that through enumerating here. I do personally kind of prefer the parser-based approach with something like nom-locate. It tends to be a little bit more flexible, and it can let me handle errors a little bit better. But in this case, this is all we need. So we get that hash set, and with that hash set, because we don't actually need to modify anything, we can just iterate over it, check all the neighbors, which we constructed our neighbors here. These are all the offset positions. So if we have a position, this is one to the right of that position, this is one to the south of that position, and so on. Iterate over that, check if it's in. If it's less than 4, then we're good. Count everything up, and that's all we need. So let's check out part 2. The elves just need help accessing as much of the paper as they can. Once a roll of paper can be accessed by a forklift, it can be removed. Once a roll of paper is removed, the forklifts might be able to access more rolls of paper. How many total rolls of paper could the elves remove if they keep repeating this process? Start with the same example. So initial state, remove the 13 rolls we found, run it again, remove 12 more, run it again, remove 7, run it again, remove 5. So we run this until we can't remove anymore. So until that count is 0, basically. And we still need the total count. So in this case, this is going to be 42. We already have everything we need here. We're going to need to do this in a loop. I think that even though it's probably not the most efficient, I think I want to return all the positions that are possible or candidates for being removed. So one thing that we might be able to do is use extract if. Extract if is kind of one of my favorite iterator functions, so I kind of want to use it just because I like using it, not because it necessarily is the right solution. But basically, this will let us run extract if as our loop and then do our test. The question is, we probably need a clone of the hash set if we're going to do that, because extract if doesn't really expect us to be accessing other segments of the hash set. So we could go into the source here, check for the iterator implementation of extract if, and see what it actually starts to do. So in this case, it's hash brown hash set as base. So that's this hash set, hash brown, hash set, which has extract if, which we can go into the source of. And we see the extract if with the function, the inner, with the iter and the table. And here's the iterator for the actual extract if that isn't just calling through to this, which does self.inner.next, which runs a function on k. So we can either do something like extract if or retain. If we do, we have to have some solid base of truth for this hash set, which basically means cloning the hash set each loop. The hash set isn't that big, so it's not that big of a deal. It's basically a bunch of I32s. The other approach that I can think of would be to only clone the values we're going to remove. So I'm going to rename this to, I think, original positions. I'm going to clone this into positions, or rather, we don't really need to do that. So let mute positions here. We're going to have a for loop, or rather just a regular loop, and or a while loop. We'll figure out what our condition is in a second. So when we loop, I am going to collect rolls to remove, positions, iter, filter, position. If this is less than 4, it's a candidate to be removed. If we collect that, we should end up with the rolls to remove. We're going to run this once. This doesn't have a type on it. We'll probably make this an IVEC2. There's something wrong with that, though, because these are references. It doesn't really matter to us whether these are references or not right now. Let's do let count equals 0 for the moment and run our part 2s, or rather test our part 2s. 0 as we just hard coded. The length of this is 13, so this is the right set of stuff to remove. And I believe for hash set, we should be able to get the difference. So we'll set positions equal to a difference b collect, which are going to be positions difference rolls to remove, which might end up needing to have us collect these into actual IVECs instead of references. Yeah, hash set IVEC cannot be built from references. So we're doing a little bit more cloning than is probably necessary here, but I'm taking the safe route. And if rolls to remove length is 0, then we break, and the count is going to be, I guess, the total number removed, right? So let mute, we'll call this removed count started at 0. Otherwise, we removed count plus equals rolls to remove dot length, and this is going to be count. We can break out of this loop with a value, but we don't actually need to in this case. So we'll just keep this little bit of state around. And we get 43 instead of 42, which is interesting. Let's do an info here for roles to remove. And let's skip our input up here now that I no longer really need it to be logged out. Let's check the problem. Of course, this doesn't give us the positions, which is just really annoying. So let's just do length, I guess, since that's the easiest thing to compare on. And this is 13, 12, 7, 5, 2, and then 4 ones. 13, 12, 7, 5, 2. 13, 12, 7, 5, 2, and then 4 ones. 1, 2, 3, 4. Oh, did I type in the... Well, you can't pass the test if the test is wrong. Let's put it that way. If the test doesn't test the right number, then that will be wrong. So let's run part 2. That took a little long, which is probably because we're doing all that cloning. But we did get the right answer, so we have a good base to start from. So let's do a quick bench here just to see what the difference is. So we're kind of slow today. It's 2 milliseconds, we'll call it. And like 50-ish, we'll call it. Definitely not the fastest solution out there. I think milliseconds is an indicator of a slow advent of code solution, whereas in many actual real-world programs, that is fast enough. And almost guaranteed that because I chose to just clone here to make sure that we didn't run into issues like removing items from this set before it made sense to, that'll be my first target for improving the performance here, getting rid of these little extra clones of all these IVEC2s. But overall, very straightforward over part 1. We have, again, all of our positions in a hash set that we parsed using this little parser. I don't know if you can even call this a parser, actually, but, you know, it counts. And then we've got a total list of the removed count and a loop. We iterate over all the positions and filter for only the ones who have a count of less than 4. This is probably also doing more work than it needs to, because if we hit 4, then we can early terminate there. This, again, does a clone. We do our check to make sure that this value is not 0, because if this value is 0, then we basically would stick ourselves in an infinite loop if we kept continuing, because we've stopped. There's no more work to do. Otherwise, we add the amount that we're going to remove from positions to our removed count, and we do the difference with positions. Now, it occurs to me, actually, that if we kept the original positions and cloned a copy to use in this loop, that we wouldn't even need to keep this state around, because we could do a hash set length minus hash set length. But let me get this committed before we take a look at what we can improve here. So our benchmark kind of shows an issue both in part 1 and part 2. I think 2 milliseconds is probably too long for this for part 1, and 50 milliseconds is almost certainly too long. So it's not just the allocations that we're doing, although the allocations do have an impact. So the question starts to become, what do we actually do to figure out where the time is being spent? Obviously, in part 2, the time is being spent somewhere in the processing and in that cloning. But in part 1, we have a parser and some processing. We do touch every position and check a bunch of positions. So one thing that we can do to sanity check and make sure that this parsing function isn't, like, I don't know, ridiculously expensive or something, is to create a parse function. And this parse function will go input string slice to a hash set of IVEC2s. And it's just going to be the same function here. Not really that interesting from an implementation perspective. And we're just going to parse the input here right at the top. And then over in our benchmarks, we can copy our benchmark here and just have another one for parse. Now, this doesn't need to be unwrapped because it's not actually, as I need to rename this function, that it can't be the same name as another function. I forgot what I was saying. Anyway, this is spending, let's call this 300 microseconds, I guess, on the parse. Feels a little slow, but it's not the vast majority of our time. So it's not really the right thing to spend time optimizing, I don't think, even though we absolutely could. We still have 2 milliseconds to account for. And 300 microseconds compared to 2 milliseconds is just not really a interesting thing. So The question becomes, if we have a bunch of positions, for example, in this hash set, how can we reduce the amount of work that we need to do to check all the neighbors? And I can't really think of a way to avoid needing to touch, I guess, at least 5 neighbors. We could early terminate. It doesn't really feel like contains should be that expensive. And we unfortunately don't really have a lot of places to put tracing information. So it does take 2 milliseconds. But if we were going to do tracing, right, we could do the span for the function and another span for the filter. But what is that really going to tell us? How big is our actual input? It's 136. I'm just going to assume 136. Like this is a square in my mind right now. So that's only 20,000 items. I guess it's 20,000 times 8 checks, right? So we're talking about like 160,000 contains checks. We do have to accumulate this hash set at some point, or we have to use the original string. If we use the original string, we can kind of avoid doing this parsing. But again, the 300 microseconds on parsing is not my concern right now. So I'm not a huge fan of the performance that we have here. We were able to break out that parser into a separate benchmark, but these times feel a little bit suspiciously slow. I don't really think that profiling will help much. I know why part 2 is slow because of the extra clones. And part 1, I think we only improve by improving our algorithm. So in this case, we iterate over all positions and check all 8 neighbors for all positions. I know that we could do this without parsing, and we could do this in one pass without parsing. We could, of course, do the classic rayon, which is a bit of a cheese. Cuts our time in at least half. We're saying that the mean is 700 microseconds. Our previous mean was like 2 milliseconds. So rayon gets us that speed up. And then now 300 microseconds starts to look a little bit stronger of an opportunity to optimize, because now 300 microseconds is half our program length. But yeah, I think that's going to be it for today. I might do a little bit more refactoring, a little bit more performance work. We'll see. But in the meantime, let me know how you did down in the comments, and I will see you again tomorrow. Okay, JK, I'm back after taking a little bit of a break. I actually think that this would be a great opportunity to show a couple of ways to profile things. So I think we're going to cover Tracy. We might cover DAT for memory heap profiling. And we've already covered Devon for benchmarks. So we're probably not going to cover that unless we make some changes. I'm really only intending to show the profiling side of this right now. So we'll see. So if we're going to use Tracy, there are probably 2 things to be aware of. One is that Tracy is located in this repo, wolfpld/Tracy. This is the official site, or rather the official Git repo. It is a profiling tool. If you don't want to run it on your own program, I believe the web has actually something you can play with. So you can see as I drag in here that it's selecting different pieces of an application. This for me is something that I use more when it comes to Bevy and trying to profile sort of a longer running application. There's a couple of really interesting, this in particular isn't a program that I know a lot about, so I don't know exactly what to search for here. But you can see that there is game loop, screenshot ready, some other stuff. The total time it's taken, I always want to call this milliseconds per tick because of Minecraft, but this is mean time per call or something like that. So you can see how there's total time of 24 seconds for the game loop. There's 1,499 calls of it, and it took on average 16 milliseconds, which sounds like 60 FPS to me. Once you click on one of these, like try door in this example, this will show you a bunch more information. I'm showing you this now because the program that we're going to see is going to have significantly less data. So I do want you to get kind of a little bit of an overview into what it might look like if your application actually had more data to deal with. The other thing is that installing Tracy and installing a Tracy client that works in your application, the 2 versions for the protocol that they use to communicate have to match. I happen to pretty much know, because I use this with Bevy, that I already have a version that is compatible with the version that I'm about to install. But if you don't, and for some reason your package manager doesn't have one, Lond did a wonderful thing for the Bevy community and started an organization that basically just runs the builds and throws them up on GitHub releases. So the latest is 0.13. If you needed something before that, you could go to the releases. There's also 0.12.2 here. That's about when this project started to produce these builds. But this is where I would generally get my releases from. Lond is someone I trust. And the crate we're going to use is called Tracing Tracy. There's another crate called Tracy Client, which I believe is a dependency of this one, actually. If you want to do, more specific integrations, if you don't want to use tracing for some reason, etc. So this is going to be 0.11.4. And I happen to know ahead of time that because these don't take that long to run, we are going to need a feature. And I forget the name of the feature. So we're going to go to the docs and I'm going to check the feature flags. And the specific feature name is called flush on exit. So if you look at the features in the README on docs.rs, flush on exit waits for Tracy to connect and read out the profiling data before the program terminates, corresponds to the Tracy no exit define, yada yada, some other things. Now that doesn't necessarily mean that this is going to be particularly easy, but we're going to start using it in part 2. And there's 2 places that we're going to have to modify this. So I use tracing subscribers default configuration. There are other tracing outputs that we haven't really talked about. Tracing Tracy collects these profiles in tracing enabled applications, which means that we have this code to bring in specifically. And I'm going to comment this out for a second and drop this in. And in our cargo toml, we'll say tracing tracy .workspace equals true. So we have our tracing subscriber, which is in this case just the Tracy layer. So we could actually stack these layers together in different ways, but we're just going to use the Tracy layer for now, make it simple. And then we already have our process instrumented. But one thing that we do need to do, and this is one of my downloads from that Tracy builds organization. So one thing that we do need to do is run the Tracy profiler. So this is the Tracy profiler. It is now open. It is not waiting for connections until we hit connect. So we will have to hit connect. So we're going to run day 4, part 2. It seems to have connected and given us some data, but you can see how small this is, right? Like we're talking like very, very small. So this is just Tracy initialization for 30 milliseconds and then quote frame 1. And we don't see anything here, right? There's no functions here, which more or less to me means that this like really didn't work. So one thing that I'm going to do is I'm going to throw a 60-second sleep into this program. I'm going to run connect again. And now I'm going to run this. And after a second or two, you should see a little bit more stuff starting to come in. Now that doesn't necessarily mean you've got the data that you want, but here you can see on the left-hand side, it says process, and that is our process function. There are some interesting things you can do here. Like if I hit source, this should show me the actual source. So you can see that process is instrumented by tracing here. If we look at a flame graph, we only have one thing. No memory data collected. That is actually a different crate that I'm not going to talk about here. So with the data capable of being collected, we can do things like let s equals span, and span is going to come in from tracing. So we'll just go up here quickly. You can see that there's more stuff coming in from tracing. I'm just going to do a star here. And info is not the name of this. If you go to the tracing docs, you can see how to define new spans. So in this case, we should have level trace or level info open to us. And this returns a guard, which we can then drop later. And I'm going to drop G right after this, at which point I am going to open another span, call this loop maybe. And maybe I'll put this inside of the loop. And now once we've collected that information into Tracy, we can start to zoom in here and you can see all of these loop calls. So here's process, right? And if I zoom in here, here's loop, 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 loop. If we look at the statistics, we can see our process is running here. In this case, it's running for a millisecond. Parser is claiming 7 milliseconds. Loop is claiming 824 milliseconds. These are obviously very different numbers than the numbers that we were seeing in our benchmark. But we can still see things like counts, and we can still see things like, on average, how long does this take? So this is every loop approximately takes 13 milliseconds in this configuration. So you can see that we are actually running this not with the release flag. So we could try it with the release flag like this, right? In which case we would open the profiler, hit connect, run in release mode, wait for it to compile because I haven't compiled it in release in a little bit, wait for the data to come in, stop, make this a little bit bigger, look at our statistics, and see that our parser is now taking 490 microseconds and our loop is taking 48 milliseconds. These are our release timings, right? When we benchmarked at something like 50 milliseconds. So this is now the correct timings. So for every loop, we're taking about 800 microseconds. And to me, it seems pretty consistent. Just scanning over here, these are like 600, 700, like high 600s, 700s. Parser is here at the beginning with an execution time of about 500 microseconds. Interestingly, the first loop takes 2, second loop takes 2. These loops are taking 2, which is really interesting. And I guess, so that makes sense. Actually, now that I think about it, what our loop is doing is removing items. So this is always the longest loop that's ever going to occur. And down here, we have the shortest loop that's ever going to occur. So the shortest loop takes about 500 microseconds, and the longest loop takes about 2.38 milliseconds. That's not micro, which is just very cool to see, right? Like, it's very cool to get this data because now we have a little bit of information that maybe we didn't have before. It's reasonable to have read the program and like inferred that the first loop will always take some more time, but to actually see it is a little bit different, right? And if we click into process, we can see the child zones and we can see that number dropping over time. So here's the 2.38 and it drops, etc. Now we don't have that many functions being called, so our flame graph is not really interesting. But if you had more stuff, it would be more interesting. So does that really give us any serious information about sort of how this happens? Maybe, maybe not. You know, we could add even more, right? We could call this filter. We run our program, we wait for the data to come in, hit stop, go to frame 1. And then when we zoom in here, we can see just how many are actually getting called. So our filter gets called actually 276,558 times. It takes about 165 nanoseconds each time it's called. But interestingly, that does seem to be where most of our time is spent. So 45 milliseconds of our execution time is spent here. Now, our loop did increase a little bit. That's not terribly unexpected because we did just send 276,000 trace messages. But it's interesting. And you can look at this down to the nanosecond resolution. See, this filter is interesting. That took 1.75 microseconds. Why? Right? We don't have all that much data about what's going on here. But why did this one take 2 microseconds when everything else is taking basically nothing? Here's another one that took a while, 3 microseconds. So as we add more spans here, we can see more stuff. I could say, for example, let count equals this. Maybe I return count less than 4. And maybe in between them, I do info or maybe trace, and I include count here. So since we'll be looking at this in a tracing application, we probably want something that's a little bit more descriptive. So maybe like filled neighbors. Run tracy, collect our trace, let the data come in, hit stop, go check for frame 1, zoom way in, and now under messages, we see filled neighbors equals 7. So now that we have some data, this is filled neighbors equals 4. This is filled neighbors equals 8. Obviously, I misspelled neighbors. Neighbords. Luckily, Tracy doesn't judge me. It only judges the performance of my code. So you can see when all these messages are coming in too, right at the top here with these little markers. Not that the number of neighbors is really going to tell us anything per se. And I'm probably being a bit gratuitous in the rerunning and looking at the code at this point, but you kind of get the point, right? Like you can set up spans around specific code blocks, you enter those spans, you can fire events which come in as messages inside of those spans and are associated with them. So when you go in here and you click on something, even something that's super small that took 250, nanoseconds, that there's messages here with the data that you wanted to trace, which is very useful. It is not particularly interesting in the sense of what we can find out about this application in particular. I think everything that we learned is pretty much stuff that you can know if you look at the program and read it, but it still is really interesting to note that there are specific timings with how long the original loop filter takes and how that decreases over time. And we can look at the actual timings. So it's nice to not have to guess around these things as well. Well, I guess I just spent kind of like 30 minutes on Tracy. So maybe we'll leave that or something else to another day. But hopefully this was interesting. I don't think it leads to a lot of insight in this particular case. I think the insight in this particular case is that there's a lot of cloning going on. There are notes that some additional functionality, such as plotting and memory allocation, are only possible as part of the Tracy client crate. These are things that are nice to have. Bevy has them when you use the tracing implementation that Bevy has. But hopefully you enjoyed a look into this. I think the only thing that I'm not really sure about is why this flush on exit flag doesn't seem to work and that we had to add the sleep. But to be fair, I'm also usually using Tracy on longer running programs. So this is not usually an issue I run into. But I hope you enjoyed a look into Tracy, and I will see you tomorrow for day 5. I think we're on.